Okay, so the goal of this particular video is to talk about inverses and how we can use compositions, which is something we've learned about previously, to prove that two functions are inverses of each other. So we already know that functions are inverses if we can switch the domain and the range and resolve one of the equations for y, and then we get the other equation back. So that's what we're doing here. We're kind of looking at those two equations, the one that we're claiming is the original function and the one that we're claiming is its inverse, and our job is to prove to people that these are inverses. But instead of turning one of them into the other and showing that they're opposites that way, we can also use compositions to do that. And so what we're saying here is that functions that are inverses undo each other. And what that means is that if we start off with x, right, that's our simplest function, and we start doing operations like adding 5 and dividing by 2 or anything like that, the inverse is going to do all of the opposites of the original function. So if the original function adds 2, the inverse function will undo that by at some point subtracting 2, right? So they're going to completely undo each other so that when we put them together and we plug one of them into the other, which is what a composition is, we're actually going to undo all of the operations, and the only thing that's going to be left behind is that x that we started with. Okay, so let's take a look at a couple of examples and we'll see what we mean. Okay, so to determine if two functions f and g are inverses, we are actually going to check the following two things. We're going to take the g function, okay, and I'm going to plug that into f, and when I'm done, after I simplify all of the expression, I should just be left with an x. If I do the opposite, I take f and I plug it into g, the exact same thing should happen. So let's take a look at some examples and you'll see it happening. Okay, so here's the simplest example. If I just have x plus 3 and x minus 3, we can kind of see that they are inverses of each other. They both started off with an x, f adds 3, g subtracts 3, so they're actually going to undo each other, adding and subtracting. So watch what happens. F of g of x, okay, means that we are going to take the g function, which is x minus 3, go to the f function right here, and I'm going to plug it in. Okay, so this means to take f of x, and instead of writing x, I'm going to write what g is, which is x minus 3. Okay, and if you see what happens immediately, not a whole lot of work here, negative 3 plus 3 cancels, and my outcome is just x. So what happened was all the operations in f got undone by plugging in g. In order for this to be an inverse, though, this has to work in both directions, which means I have to take the g function and I need to be able to plug f into it and have the same thing happen. So I'm going to go to the f function, which says take whatever function you're plugging in, subtract 3. Well, I'm going to plug f in, and it's going to look like x plus 3 minus 3. So again, this is a pretty obvious result. If I'm doing 3 minus 3, that cancels, and I'm just left with x. This is the result we're looking for. I need to do f of g of x and g of f of x. And in both cases, after I do all the simplifying, I need to get an x as my result. Okay, so here's a slightly more complex example. I'm going to make one quick adjustment. This is supposed to be an x here, okay, not a y. Okay, so what we're going to do at this one is we're going to do the same thing. So we're going to check, and we're going to do f of g of x. Okay, and again, what that means is that I'm going to take the g function, which is this thing, x minus 3 over 2, and I'm going to put it right there in the f function. I'm going to put it in for the variable. Okay, so here's what it looks like. Okay, 2 times x minus 3 over 2 plus 3. Right? So we can kind of again see the same thing happening. Like in the f function, I'm doing times 2, and in the g function, I'm doing divided by 2. In this function, I'm doing adding by 3. In this function, I'm doing dividing by 3. So we're going to actually see all this cancellation happening. If you notice, I'm doing 2 times, and then I'm dividing. So dividing by 2 and multiplying by 2 are opposites. They're going to cancel. So what I end up with is x minus 3 plus 3. And again, negative 3 and positive 3, those are opposites of each other. They will cancel, okay? And my result is going to be x. So that is what I'm looking to happen. Let's just make sure it happens for g of f of x as well. Right, so this means let's go to the g function, that's this one, and I'm going to say this is now, instead of x minus 3, I'm going to plug f in there. Right, that's what this says to do, take f, plug it into g. So it's going to look like 2x plus 3, okay, that was x, minus 3 over 2. Right, so I went to the g function, I plugged in 2x plus 3, and now let's simplify. So the first thing I can do is let's simplify the numerator. I see plus 3 minus 3, that's a cancel happening. So these are going to go away. Plus 3 minus 3. So now I'm left with 2x over 2. Well, the 2 and 2 divided by 2 will cancel, and again, I'm just left with x. So I can say, yes, these are absolutely inverses because when I compose f with g and I compose g with f, In both cases, all of the operations cancel, the variable stays around, and that's the only thing that's left. Okay, so I want to look at one more, slightly more complex example, and that's using squareds and square roots. So those are opposite operations, so it makes sense that they would be inverses of each other because squareds and square roots cancel each other out. So let's check the f of g of x. F of g of x says, let's take g of x, well, that's this thing, okay, and let's plug it into the function. Let's find out what happens. Okay, so this says now the square root of x plus 2 squared minus 4, that was x, this whole thing, okay, now I need this extra plus 4 that was already there, okay, minus 2. Okay, so if I start working underneath the radical and simplifying, I'm going to say, okay, well, negative 4 and 4, they cancel. So now I'm at x plus 2 squared, okay, and the square root's still over that, and then the minus 2 is just on the outside by itself. Well, squareds and square roots cancel each other out. There's nothing else floating around out here, so I can cancel the squared and the square root, and now it's just going to look like x plus 2 minus 2, and I get a 2 minus 2 cancel. My final answer is x, right? So everything in the g function, when I put it underneath the radical, canceled out all of the operations that existed in f. The only thing that's left is the variable. That means that it is an inverse. Okay, so let's make sure it works the other way around, because this needs to work for also g of f of x. Okay, so I'm going to go to the g function, and in this space right here, I'm going to put this whole big expression. So here's what it looks like. I'm going to say the square root of x plus 4 minus 2, right? That's x. Okay? And then I'm going to have to add 2 to that. Okay? And then this whole thing gets squared minus 4, right? So this piece right here, x, the square root of x plus 4 minus 2, that was x, right? And then I just kept going with the rest of the g function. So let's find out what happens. Again, minus 2 plus 2 cancel. So now my problem looks like the square root of x plus 4 squared minus 4. I have that same situation happening. Square root and squared cancel each other out. So they're both going to go away, and I'm left just with the x plus 4 that was under the radical and the minus 4 that was by itself the whole time. And there's my last cancel. Okay? So all of the operations in squareds and square roots and the plus and the minus and the negative 2 and the positive 2, they all cancel each other out. And in both situations, f of g of x and g of f of x, all of the operations canceled. My result was just the variable x.